purpose of my project is to design and build an accelerometer. Talk about how that would work. So, hello world, this is Dr. Horvath here, doing a physics final video on acceleration. So, what is acceleration? By definition, acceleration is a change in velocity over a given period of time. So, common examples are gravity, as it pulls you down at negative 9.8 meters per second. This is found in nature. But if you want something not natural, you can use your parents stepping on the gas right before a yellow light to make sure they don't hit the red light. The force you feel pushing you back on your seat is acceleration as the car is getting faster, so change in velocity. Acceleration is, in most senses, constant, but there are cases when acceleration can be nonlinear or can have a slope, and that would make your velocity change even faster, so you'd notice a greater effect, kind of like, say with the example of a car, you'd be sitting down and you'd notice a small force and the force would be getting greater and greater. Under normal constant acceleration, you wouldn't feel a greater force, you would just feel a normal force. But if the acceleration was nonlinear, you would get pushed more and more against the seat. Or like say gravity, it's at a constant 9.8, but if it were to be changing upwards, you'd be getting heavier and heavier. And it also works oppositely, so if it were going the other way, you'd be getting lighter and lighter if it was non-constant. Or if it was constant, you'd actually you'd kind of have zero gravity pretty much. So, yeah, let's go to the whiteboard, shall we? So here we are at the whiteboard. So now let me go ahead and explain to you all of the math and theory and fun stuff. So, how would you make an accelerometer exactly? My idea was you have a string suspended with a weight on it just to keep it horizontal. And you'd measure whatever angle it moves in. Then you could use that in a trigonometric ratio to figure out all the other stuff. So, say you'd have the string. Then you will always have gravity, so it'll be going down at, it's an arrow, at 9.8 meters per second squared, right? And if there's nothing going on here, then there's nothing to move it past. So if you were to measure the angle from the vertical, it's 0. In both directions, it is 0. So 9.8, which means nothing going this way. Now, the way you'd measure it is you'd have your pivot point, which would be right here on this one, and then you'd have your string, and say it were to be going like this, the length would stay the same because the string doesn't grow or shrink. The weight would stay the same because that doesn't grow or shrink either. But due to gravity, you will still always have the 9.8 acceleration vector. But say it were going also at 9.8 acceleration or meters per second squared that way, then you could measure the angle from the vertical, and this angle in here, theta, would equal 45 degrees. Because we know that on a 45-45-90 triangle, both of these are the same. So you can set up your equation, and since this is the same, you don't have to care about it, and all you really want is this. And if you want to do like a triangle type thing, then you could just flip it around a little. So there's your pivot point, here's your thing, there's that. Here's gravity at 9.8. And then here's your horizontal vector at 9.8. Then here would be your angle. And it looks a lot like a trig triangle. So you could use tangent since it's both of these sides. So you would say tan of theta is equal to, and this being theta here, is equal to, and then it's always the y over x, so 9.8 over 9.8. So tan 0 is equal to 1. And then if you were to inverse tan it, then you'd get theta is equal to 45 degrees. So that's correct. Now that's how you could find the angle it would move at a certain acceleration. So that way if you want to hit a certain acceleration, you just gotta plug it into here. This bottom one being your gravity, and the top one being your horizontal vector. So say I wanted to hit 13 meters per second squared horizontal acceleration, I'd say tan of theta is equal to 13 over 9.8, and then solve for theta. But say you've already got your angle, but you don't know what the acceleration is, like say you're sitting in a car and you want to figure that out. Well then, you could do something similar. So if this, so now we could just say this is 45, and since we flipped over the triangle, this up one is your horizontal acceleration, and then this would be, say, x. So now we again put this into our trig ratio, and it would be tan of 45 is equal to, then it would be x over 9.8. And then if you want to solve it, just multiply 9.8 to both sides, so it cancels out here, 9.8 times, and then that equals x. And if you want to see the other equation for finding out the thing, instead of just seeing the trig ratio, it would have been 10 negative 1 of your x over 9.8 is equal to the angle that it would go at, or this. So this would be used to find the angle, this would be used to find the vector. And you're probably wondering, does the weight on the string matter? In reality, no, because it will stay a ratio. So say you had a mass of 2 kilograms on the string, and this would be your 45-degree angle, and this would be equivalent to 9.8. Then you'd multiply the 2 kilograms times 9.8 meters per second acceleration, and you'd get a big number. But the thing is, these would both be the same, and tan 45 is equal to 1. So you'd have the same over the same, and that's equal to 1. So in reality, no, the mass of the weight does not matter. It's just used there, so the string's not just blowing around from wind and stuff, so it actually stays down. And the way you can build something like this is you get like a protractor with all of your little angle markings on there, and then you tie a string and hang a weight to it. And then that way, when it moves, you would just figure out, like say it would move to here, you would just figure out what this angle is, and then you can plug that into that one angle formula I showed, or that formula to find out what this is equal to. So again, remember that was tan of theta times 9.8, and it's like this, not theta times 9.8, then tan, it's tan theta, then 9.8 is equal to, and then your x, so x. So beautiful. Let's see how this works in real life. Okay, so I built the device, the accelerometer, and here's the protractor with the nearly massless string and a lead weight. So, let me go closer so maybe you can see. So yeah, pretty much it's, you have to count from 90, pretend that's like your 0 angle. So since there's no horizontal motion, the angle is 0. Let's say I were to go like that, I gave it acceleration, or like that, I gave it acceleration, and that's why it moved. Now, I can't really test this without being in like some kind of a rocket sled or some fun equipment like that. So, unless I were to impose acceleration another way. So one way that I can do it is by spinning around, because we learned that acceleration is caused by velocity squared divided by radius. So all I would have to do is take measurements and stuff to figure out what I would do. So I'm going to say, for the sake of simplicity, let's try to do around 13 meters per second acceleration, which I've already done the calculation for that, and it should give me around 53 degrees. So I've also already tested this, so I know it's extremely hard to measure the angle while you're spinning around. So I've got another way to test it out, but first let's try it with this. Yeah, let's do that. So here I have the accelerometer, and now here I've got my trusty stopwatch of science. So we're going to use the equation acceleration equals v squared over r to see if everything matches up. So r, when I hold it out like this, would be measured from here to the string, which is 0.86 meters or 86 centimeters. And velocity is going to be measured by multiplying the radius by 2, multiplying by pi, and getting the meters and finding out how long it takes to go 1 revolution, and that should give me approximate velocity. So I want to get a 13 meter per second acceleration. So when you put that into the equation, it would give you an angle of 53, which would be here. So let's see how good this works. I'm going to spin around and start timing. When you hear the beep, that means I started timing. I'm going to do time 5 revolutions to get more average and accurate results. And then we'll plug it into all the equations and see how that works. So yeah. Okay, 7 seconds 41. I'm not sure how accurate this is because I'm so dizzy and it's really hard to get the to even see the angle when you're spinning around. So, but we'll still plug it into the equation and see what we got. So, yeah. Okay, so I did all the calculations and took notes. The radius was 0.86 meters, as I pointed out previously. The time it took me to spin around 5 revolutions was 4.71 seconds. The number of rotations I did were 5. So if I want to calculate velocity, I would have to get my radius, multiply it by 2 to get diameter, then multiply by pi to get my circumference, which was 5.4 meters. And then once I get that, I can plug it into here. So 5.4 meters times 5, because I did that many revolutions, divided by the time it took me to do 5 revolutions, and that gave me about 3.64 meters per second average. So then you can plug that into your A equals v squared over r formula. So you'd have 3.64 squared divided by 0.86, and that would equal about 15.4 meters per second squared. So I was going for 13 meters per second squared, which would have given me a 53-degree angle, but I think I kind of overshot it, being dizzy and whatnot, after having to do that one clip 3 times because I failed the first 2 times. So I then did the math, plugged it into the trig equation from the beginning, and found out that the angle that something like this would give me is 57.53. So I said I have to get it at 53. I went 4 degrees over, so that's actually not too bad. It was really close, so I think it would have worked. Like, all the mathematical evidence indicates it would have worked. So, yeah. I also tested this out using a robotic ball that I have, and it came out quite nice. So, that's pretty much it. Thank you for watching my physics final video. This is Dr. Horvath signing out.